Hello, my name is Abby, and my partner for this presentation is Shin, and today we will be talking about reliability and survivability in JUMP. For the bladder cancer dataset, we will be doing recurrence analysis. Recurrence analysis is used when the events can recur several times for each unit. These events occur when a unit breaks down, is repaired, and then put back into service after the repair. This can also be used when analyzing data from continuing treatments of a long-term disease. The goal is to obtain the mean cumulative function, which shows the total cost per unit as a function of time. With the bladder cancer dataset, we are trying to see whether the drug the patient is placed on has a significant difference. Here is the bladder cancer dataset, and with this we will be doing recurrence analysis. So we can either go to the script that they already have up here and run it, but however, we want to do this by ourselves, so we will go through that really quickly, but this is what we will want in the end. So we can go and edit the script to see what they want for each point on the recurrence analysis platform. So we go to Analyze, Reliability and Survivability, and Recurrence Analysis, and then we can pull up the script right next to it and see what goes where. So on Y goes the age, and cost goes to cost, and the treatment group goes to grouping, and then the label system ID is the treatment number. And once that's settled, we can click OK. And now we can see that we have what we had before. Looking at the event plot, it is color-coded based on the treatment. The dots represent a checkup on that patient. If there are no dots or there is no line after the last dot, that means that the patient has died. We want to look at the MCF plots to see if there is any difference between the drugs. If the confidence intervals do not include 0, the treatments are then considered to be convincingly different. But as you can see in all three plots, they all include 0, meaning that there is no significant difference among the treatments.
According to the textbook, life data analysis, also known as life distribution analysis, is the process of analyzing the lifespan of a product, component, or system to improve quality and reliability. You can observe failure rates over time to predict when the product, component, or system will fail. This can be used to determine warranty periods as well as determine the best material and manufacturing processes for the product. We can use sensor data, which means sometimes the exact time of failure is unknown. The fan dataset, we want to see which distribution most likely fits the failures of the fan so we can later predict the failure times of the engine fans.
So this is the fan dataset, and with this we will be doing the life distribution. So we will go to Analyze, Reliability and Survivability, and click Life Distribution. And time will go on time to event, and sensor will go to sensor. And from there we will click OK. And first thing we want to look at is the event plot, and we will look at this later. And then next we will scroll down and click the log normal and the corresponding scale. We can see that the confidence intervals line up, and then we can scroll down and see the statistics report.
Looking at the event plot, the dotted line indicates that the fan did not fail from the last time it was checked onward. If the line stops and there's a dot on it, as seen in Unit 24, this means that the fan failed at the inspection. As we can see, the data most likely follows a log normal distribution. We can look at the statistics report to look at the model comparisons, profilers, and more. We can compare the AICC against other distributions, and whichever AICC is the lowest is the most accurate distribution for that dataset. Next, we can look at the profilers, and we can see that they are useful for visualizing the fitted distribution and estimated probabilities. As we can see, the quantile profile here tells us that the median estimate is 25,418 hours.
Thank you for watching our video.